Hello, and welcome to the final presentation of the end of the year project in class EEL 6562, Image Processing and Computer Vision for fall semester 2013. My name is Alan Stark, and I'm a first year graduate student aiming to receive my PhD. Without further ado, let's get started into this presentation. So, the key reason of this project is for the user or student, me, to grasp and demonstrate their comprehension of the knowledge relating to motion-based or object-based tracking, implementing the kernel tracking and point tracking procedures. General research has been conducting on both techniques of kernel tracking using mean shift method and point tracking using Kalman filters, and these both will be explained further in this presentation. Motivation for this project includes interest in robotic design and development for security and surveillance purposes. Robotics is as a growing field in research with the addition of boundless sensory networks that produces efficient results based on the best data processing techniques. Robotics could be used for a plethora of different applications such as security and surveillance. Also, as you can see, security and surveillance on a building, unmanned autonomous vehicles, or satellites. Again, the purpose of this report is for the comparison of image processing techniques in order to determine, in my opinion, the best from this experience or experiments. There are many other methods that can be used for object or motion tracking, including but not limited to Lucas Tomasi, which makes use of spatial intensity information to find the position that has the best match. High transform algorithm, which this technique finds an imperfection within the image by using a voting procedure where moving objects are obtained through local maxima, and also joint probabilistic data association filter approach. And this approach takes all potential candidates and join them together in a single statistical most probable outcome. For this project, though, I'll be doing my experiments with only two methods, and these methods include mean shift and Kalman filters. The mean shift method is a non-parametric feature space procedure used for cluster analysis in most image processing techniques. Object tracking using this method is a two-part process consisting of the production of candidates and their assessment. And then I'll be using Kalman filters, and Kalman filter procedure uses recursive algorithms and state space techniques to predict the next path of the moving object. The Kalman filter equations comprise of two sets involving time update equations that obtain the estimates for the next time step, and measurement update equation that controls the feedback, and I'll be explaining these equations a little bit later. So first off, let me give you a step-by-step process of the methodology into implementing these methods for object tracking. First, we'll go through mean shift, then we'll touch into Kalman filters. So for mean shift, the first method is the most important, which is importing the movie, which this will give the code the length, height, and width of each frame in the movie inputted. It will also insert the frames, all frames of the video, into the variable movie, or any variable that you would like to assign. Step 2, define and set up the parameters for the kernel weighting. The set of histogram values is weighted by a Gaussian kernel to yield a smooth set of values. Step 4, define the position of the target through the estimation of the image. The object that was selected from the user also accompanies this step. And step 4, use mean shift method to determine the location of the object selected by the user in the next frame and draw a box around this new location. And the mean shift method accomplishes finding the next path by determining the best match of the target by maximizing the Batachary coefficient. Excuse me for ruining that name. Where this coefficient is represented as below for two statistical distributions, P of Z and Q of Z, which are the histogram distributions of the target and candidate. As you can see, the mean shift method maximizes this coefficient by maximizing the second term here, where H is the kernel smoothing parameter and omega is the weightings defined here. The terms QU, Q sub U, and P sub U are the values of the target candidate's histograms corresponding to the pixels X of I of the candidate object. The center of the target is then calculated by this following equation here, where y naught is the current location of the candidate center and g sub x is the derivative function. And to get a better demonstration of this algorithm in the code form, so the purpose of this slide is to help to give the viewer a more in-depth insight on how mean shift method was implemented in this code. The beginning of this section is just a bunch of variables being updated, but when we get to the for loops, this is actually where you can see the summations happening for the calculations for the new positions. As you see, this section is the same as the equation shown to you from the previous slide, or as you can see in the top right corner. Here, the code calculates the numerator of this equation for x and for the y position. So this will be xi, will be trying to calculate this portion just for x. So replace these with x. And then also trying to calculate this portion with the y coordinates. Then the bottom denominator here is calculated. And to determine the new paths for x and y, the numerator and the denominator are divided here to find d sub x, dx and yx, which are the new projected paths. Y and x here are the new coordinates, which are the addition of the projected paths plus the O coordinates. Now we go on to a step process for the Kalman filters for object tracking. So the first step is importing an input video and extracting all frames to save in the folder under the current directory. The frames are extracted in color, but also can be extracted in grayscale. Step 2, finding the background image of the set of images in the frame is done by obtaining the first 20 images and using those to find the mean image, which you would take as the background image. Step 3, you subtract the background image from the current image and add a Gaussian filter to smooth the values. In step 4, you take that and threshold it to obtain an image that identifies the moving target. This image is usually identified, or the moving target is identified by a red diamond. And in step 5, you perform Kalman filter to predict the next step of the moving object using the previous state and the predicted motion. So let's go on to the actual Kalman filter algorithm. which Kalman filter procedure uses recursive algorithms and state space techniques to predict a path. Equations comprise of basically two sets involving the time update equations that obtain the estimates for the next time step and the measurement update equations that controls the feedback. As you can see, the Kalman filter functions recursively from this image on sequences of noisy input data to fabricate a statistically ideal approximation of the essential system state by computing the Kalman gain here, updating the estimates with previous data here, computing the error covariance here, then projecting the new path here. And now we can see how this is actually implemented in code. From this code, the viewer can still see the loop that each frame must pass through in order to calculate the object's next move. First, you see the prediction of the next step of the object with the last state and a predicted motion. Next is predicting the next covariance, as you can see here. And also you can see the code barely deviates from the flowchart as the Kalman gain is being calculated here. And then again, the update state estimate and covariance estimation here. After running the code, the left image is a single frame demonstrating the ball being tracked by the red box. So you can see a red triangle here tracking that ball. This mean shift method had no problem with tracking objects of different sizes. In fact, with the code used, the user is able to specify the area or object they would like to be tracked. This method has no problem tracking different color objects because, like I said, the user can specify which object to track. This method can track objects moving in different speeds, but also may have problems with objects that accelerate too fast. The big jump in the speed of objects tend to make the tracking box to lose sight of its target. This method can track objects in a nonlinear path, but as I said, if the nonlinear path is too sharp, the tracking box will lose track of its target. Also, with multiple objects to track, this method was able to track only a single object that we specified out of amongst a few objects that were moving. And you can see that the time elapsed for this tracking method was 8.11 seconds and approximately 18 lines of code just for the processing of mean shift. Next, you can see the Kalman filter. This is the raw image, background image, Gaussian, smooth, and threshold images after running the code, and I'll also show the image of my hand being tracked next. But this code had no problem tracking objects of different sizes, no problem tracking objects of different colors, and no problem tracking objects of different speeds or nonlinear trajectory. The biggest problem is it could not track any objects with multiple objects moving because it couldn't decide which object to track, so it was basically jumping between the two. And the time ran is 5.9 seconds and 14 lines of code. Here's my contribution. To the left is the 2D Kalman filter without the addition of my code, and to the right is the 2D Kalman filter with the addition of my code. And basically all my code does is just take the background image of the colored images so that when you're running tracking, you can actually display the color video or the color object being tracked instead of just a black and white object. In conclusion, both methods have their pros and cons, in which each method would be best suited for different particular types of object tracking. For example, the mean shift method will most likely be used for tracking of a single object within the midst of other moving objects. From my experience, Kalman filter object tracking method would be best suited for motion detection tracking. From this experiment, I conclude that I would prefer the multiple object tracking using Kalman filter method for motion-based tracking. This would be perfect for video camera surveying a building, and in other cases, I would prefer mean shift tracking to add to an autonomous unmanned vehicle that could possibly track single targets within big clusters of moving objects. Here are my references, and at the bottom is a link to my video for my demonstration of these two methods, and that is the end of my video.